we need to learn about axial and lateral resolution, what they are and exactly what that means to us as sonographers. Resolution is the ability to discern physical characteristics in any of the three dimensions. So when we say axial, we mean along the direction of propagation, so from the transducer to the deeper tissues. Lateral resolution is side-to-side resolution, so the ability to separate them along different paths of sound. So if we send a sound beam in and then we move over and send another one in and listen to the echoes come back, that different side-to-side is what we consider the lateral resolution. Now, elevational resolution is the thickness of the sound beam. This is when you hold your probe down transverse to the body, it's the portions above and below the probe, so up towards the head and towards the feet, not side to side, that is being able to be resolved. So this is the actual thickness of the sound beam. So axial resolution is, as I said, the ability to display two structures that are close together along the sound propagation. The closer the structures are to each other, the better, and we can still discern that they are separate structures, the better the axial resolution. So we want to get two structures as close together as we can and still know that they are distinct structures. Now, with axial resolution, we can ask the question, what is the minimum distance that two structures positioned parallel to the sound beam can produce two distinct echoes on an ultrasound image? And the answer to that is the spatial pulse length divided by 2. So the axial resolution is measured in units of length, and the smaller is better. The closer together two reflectors are, and you can still distinctly tell them apart, that's better. That is determined solely by the spatial pulse length, and as you know, the spatial pulse length depends on both the sound and the medium because it's related to the wavelength times the number of cycles of the pulse. So in that fashion that it is the number of cycles, it is also related to the pulse duration. The shorter the pulse duration, the better the spatial pulse length. We have several synonyms that we utilize when we're discussing axial resolution. So we have depth resolution, along the axis of propagation, that's going deeper into the body. So we call that the longitudinal. Remember, these are longitudinal mechanical waves, so that's along the propagation path. It's the axial resolution. It's along that axis of propagation. We also call it the range or the radial resolution for archaic reasons, and also the depth resolution. So it comes to this mnemonic lard that we can use to remember these different synonyms that come up. What is the range resolution? Well, it's the axial resolution, SPL over 2. It is not adjustable by the sonographer. It's set by the manufacturer. Typical ranges are 0.1 to 1 millimeter, though they can vary. The shorter pulses are created by the backing material. Gives us less ringing, fewer cycles per pulse. And the higher frequency. Each cycle itself is shorter, so that gives us better axial resolution. So we'll summarize that. When we look at low frequency, we have long wavelengths. Okay, so if you count 1, 2, 3, 4, 5 cycles, high frequency, we have the same number of cycles as this low frequency one, but it's a much shorter pulse length because each wavelength is shorter than in the low frequency. The number of cycles makes a difference. So we have 5 cycles here. That gives us a distance from the start to the finish. Here we have fewer. We have 3 cycles. So it's only, you can see it's much shorter. Lateral resolution is the ability to distinctly identify 2 structures sitting close together when they are side by side. So structures that are perpendicular to the main axis. When I say main axis, that is the propagation direction, the propagation of the field of the sound beam. When we look at lateral, we're talking about perpendicular to that main axis or side to side. And so we say lateral resolution is what is the minimum distance that 2 structures positioned side by side can still produce 2 distinct echoes on the ultrasound beam, on the ultrasound image, excuse me. The units of lateral resolution, because we're dealing with spatial resolutions, are length, of course, in millimeters. Smaller is better. And lateral resolution is determined by beam width. Whatever the beam width is, that is what the lateral resolution is. So we have several synonyms again for lateral resolution. We have lateral resolution, angular resolution, transverse or side to side resolution, and something called azimuthal resolution. So angular and azimuthal are both archaic terms that have to do with single crystal transducers that we used to use back in the 60s, 70s, and 80s. Lateral resolution is always best at the focus of the beam. It's always considered good within the focal zone. The axial resolution is always a smaller dimension than lateral resolution, so axial resolution is always better than lateral resolution. So reflectors closer to each other than the beam width will show on the screen as a single reflection. Okay, so anything closer together than the beam width shows up as one reflection, which means we can't resolve it. We can't tell that it's actually 2 structures. Things that affect lateral resolution, the aperture of the crystal, which is another way of saying the crystal diameter or the crystal size. Harmonics affect the crystal resolution, so we haven't talked about harmonics yet, but just remember that a narrower beam diameter occurs with harmonics. So because the beam diameter is narrower, the lateral resolution is better. Remember, beam width or beam diameter is lateral resolution. And then frequency. As we increase frequency, it extends the length of the near zone and the focal zone and improves lateral resolution in the far field. And beam diameter. So again, as the narrower the beam is when we start out, that is better lateral resolution. Beam diameter is equal to, it is lateral resolution, and it does vary with depth. So let's summarize what we just said. Axial resolution is along the axis of the beam, along the path of the sound beam. Lateral resolution is side by side or perpendicular to the sound beam. Our mnemonic for remembering axial resolution is LARD. Our mnemonic for remembering lateral resolution is LATA. LATA, lateral. The axial resolution is determined by the pulse length. The lateral resolution is determined by the beam width or beam diameter. Axial resolution is changed by changing the frequency or changing the transducer or whatever the manufacturer sets it at. It does not change with depth. That's a very important factor. Axial resolution does not change with depth. It's the same at 1 centimeter as it is at 50 centimeters. Lateral resolution absolutely changes with depth. The beam shape changes with depth, so lateral resolution changes with depth. Axial resolution is best with a short pulse. Regardless of whether you're in the near field or the far field, the short pulse makes axial resolution better. Lateral resolution in the near field is best with a small diameter transducer, and in the far field it is best with a larger diameter transducer and the highest frequency you can use. So these pictures depict axial resolution is along the beam path, lateral is perpendicular. Elevational is the thickness of the beam. Structures along the beam axis are separated, and we call that axial resolution. Structures side by side either can be separated. In this case, we're able to resolve two structures, and we see them as two structures, or in this case, we see them only as one structure. They're the same distance apart, but this one's in the focus. This one down here is in the near field, and the beam is simply too wide for them to be resolved. Okay. Focusing transducer, a flat crystal naturally focuses to an area we call a focus. It uses what we call near field effects or Fresnel focusing to focus down to the minimum diameter. This is called unfocused ultrasound. This is a flat crystal. We call it unfocused ultrasound. It has a natural focus. If we change any other aspect of the crystal, we're going to call it focusing or focused ultrasound. Okay, this becomes important with bioeffects. So flat crystals, unfocused, but it still naturally focuses. Okay, so focusing concentrates. Focusing is a technique we can use to apply to the transducer to actually concentrate. Focusing concentrates the energy into a narrower beam and improves lateral resolution. So there's really three ways of focusing the beam. We're going to say there's four ways if we include the diameter of the beam. So there's external. We can put a sonic lens on the front of the transducer and focus the beam. This is called a fixed mechanical focus. We can do what's called an internal focus of the beam, and this is where we actually cut and curve the element so that it's fixed at a particular point, but it is focused because of the curve along it. Then there's something called phased array, which is electronic focusing. We haven't talked about what phased array is yet, but this is what we do every single day when we use transducers that we just pick up and place on the body. These are all phased array transducers. They are adjustable and they are electronic. So how can you tell us if it's a phased array transducer? Is it adjustable? Okay. If your transducer, if your machine has an adjustable focus, it's phased array. There you go. And then the other way of focusing is changing the diameter of the crystal. We call this changing the aperture. Okay. So some authors will say there's only three ways: internal, external, and phased array. Others will say, yeah, but changing the diameter of the crystal also changes the focus. So I'm going to go with that. The aperture can change. That gives us both adjustable electronic focusing in both a phased array and something called an annular array. And we'll talk about annular array on some other day. You don't need to know what that is. However, if you want to Google it, it's there, right? All right, focusing. So we have several Fixed focus techniques.
Let's discuss these different fixed focusing techniques. One is the conventional or mechanical focus, and this is where the lens is just flat and focuses through near field effects. The next is the with this, the focal depth and focal zone are set by the frequency and diameter of the crystal and cannot be changed. Sometimes the manufacturers will add an external lens onto the transducer, and this will then focus the beam closer to the transducer than the original unfocused foci would be at. So with an external lens is placed on, this will then focus the beam. You can also have an external mirror focus where the sound is reflected off of a curved structure, and this also will focus the sound. These are no longer used, but this is another way of doing it, is to reflect the sound off of a focused mirror. There is a technique called internal focus, which is where the actual crystal is curved to concentrate the sound beam at a focus. With the phased array transducers, we use electronic focusing to do this, and so an electronically focused sound beam will a small element will be fired off by the pulsar. So the pulsar will fire off a small wavelet in one element, and then that wavelet will propagate out, and then the one next to it will fire off, and that sound, the original first one that fired off, will then continue to propagate out. The second one will then propagate a little bit, and then they'll fire a third one, and they'll continue doing this on down the line until we have the first sound beam from the first crystal has expanded out, the next one expanded slightly less, the next slightly less, forming a wavefront using Huygens principle, and that wavefront will then move perpendicular to itself. The propagation is perpendicular to the wavefront. So this is a way of steering the sound beam without actually moving any of the transducers. We can do the same thing by firing off crystals simultaneously on the outer part of the transducer, and those will then again propagate out a little bit as we fire the next one. Next crystal is, this will represent a voltage coming to it. And then the next one will have a voltage come to it, causing the transducer to affect the piezoelectric effect. It will fire out. The original two that were already propagating continue to propagate. And eventually it forms, again, a wavefront which moves perpendicular to the front. So the movement is perpendicular, but because it's coming in opposite directions, it causes the beam to focus down into a very narrow focus. So here's a pictorial demonstration of that same thought. So we have the unfocused flat crystal, the internally focused curved crystal, a crystal with a acoustic lens placed over the front of it, and an electric phased array transducer. So we have these different modifications to the beam. So the beam diameter, when you focus it, the beam diameter in the near field narrows. The focal point will always move closer to the crystal. The near zone is always reduced. It never extends. And the beam diameter beyond the focal zone widens. Therefore, focusing always improves the near zone and degrades the far zone. The size of the focal zone itself is always reduced with focusing. So here is a summary of our beam features. This is the characteristics, and these are determined by, so the beam frequency in continuous wave is determined by the pulsar or the beamformer of the ultrasound system. So the frequency of the pulsar is the frequency of the continuous wave. The frequency of a pulse wave ultrasound crystal depends on crystal thickness and the speed of sound in the crystal. The focal length, or the distance from the transducer to the focus, depends on the diameter of the crystal and the frequency of the sound. The beam divergence in the far zone depends on the diameter crystal and the frequency of the sound. The lateral resolution at any point in the image depends entirely on what the beam width is at that depth. And this concludes the presentation.